All right, we're going to start where we left off with the notes from last class period. And improper intervals is where we're beginning. So we left off with the second example. And so we start first realizing that it's improper with that infinite limit. And so we must rewrite it with a limit. So we're going to let b approach infinity of the integral from 1 to b of e to the negative x dx. And then we're going to realize that we know the integral of e to the negative x it needs a little adjustment because we think about u being negative x and the derivative being negative 1 dx. So we make the adjustment with a negative 1 inside and a negative 1 outside. And then we can go ahead and integrate. So I have the limit, ran off my page, limit as b approaches infinity of negative e to the negative x from 1 to b. Again, because inside here is e to the u times du, which integrates to e to the u, and with the negative from out front. Now we're going to evaluate using the fundamental theorem of calculus. So we've got the limit as b approaches infinity of negative e to the negative b minus negative e to the negative 1. So I think that I probably should write this without negative exponents. That will be helpful. And so I get negative 1 over e to the b in this piece. And I have plus 1 over e to the 1 here. Now, if we plug in or think about what's happening as b gets really large, this denominator is going to get really, really large, which is going to allow this fraction to go to 0, which allows our limit to go to 1 over e. So if we have a limit that exists here of this improper integral, then we have a convergent improper integral. So this one converges. Now this isn't the value that it converges to, or is it? So I guess this answers the question that I asked you on the other page when I said let's find what that 0.37 whatever number it was, what that 0.37 number was, exact value. If you put this in the calculator, that is 1 over e. Next example. Same process. We know how to integrate 1/4 x in that power of e. I just would have to adjust with a 1/4 inside here and a 4 outside and with a limit. So here we go. So we're going to let the limit as a, since that's the bottom number, approaches negative infinity. So from a to 0. And we know that we're adjusting with a 4 and the 1/4 e to the x over 4 dx. So that integrates into, with the limit as a approaches negative infinity, of 4 times e to the x over 4, evaluated between a and 0. Next step, limit as a approaches negative infinity of, let's plug in the values, of 4 times e to the 0 minus e to the a over 4. And now we simplify a bit. We get the limit as a approaches negative infinity of 4 times 1 minus e to the a over 4. And now we think about this negative infinity being placed up here in this fraction. So if I think about very, very large negative numbers divided by 4, we're going to still get very, very large negative numbers. And if we raise e to a very large negative number, that pretty much is going to go to 0. And so we end up with 4 as our limit out of this. And that means that this improper integral converges. And in fact, converges to 4. All right, finally, we have an example on here about finding a volume. So we think about what e to the negative x looks like, and we should probably graph it. And so I'm going to get out of this and graph e to the negative x so that we know what it looks like. Most of you should already know what it looks like, but we're still going to kind of get it on the screen here to get a visual. So y equals e to the negative x, and I'm going to zoom 6 this thing and see what I have. So that looks like exponential decay, and we were interested in that graph going between, let R be the region in the first quadrant, so the piece over here, between the graph of f and the x-axis, and then we're going to revolve this around the x-axis. Excuse me. So if we kind of sketch that graph, let's get the pen working again. So I would have, again, we're interested in the first quadrant piece, and starts up here at 0, 1, and kind of comes down here. So we're interested in finding this area being revolved around that x-axis. So we know we have sort of a disk method because there's not a hole in this region here. It sits right against the axis of revolution. So let's think about what our integral would look like. Volume is going to equal, all right, so back here after a pause for the volume, and we know we're going to start at 0 and never end here. And we have to think about our revolution, so we have the pi r squared concept and the thickness. So our radius is going to be the value from here back to that x-axis, which is my function. So I've got e to the negative x here. So then I am going to start working on this with the limit idea. So I have the limit as b approaches infinity of pi times the integral from 0 to b of e to the, I'm going to go ahead and say negative 2x dx, and then I'm going to think about the integration here. If I've got a power of negative 2x in this, I'm going to have to adjust with a negative 2 inside and a negative 1/2 outside. So I'm going to go ahead and do that. Limit as b approaches infinity of negative 1/2 on the outside. So I've got pi over negative 2 from 0 to b, and I put the negative 2 inside to adjust for the u substitution. Now we're going to integrate and get limit as b approaches infinity of negative pi halves, and the integral should be e to the negative 2x evaluated between 0 and b. Now I'm going to plug in. So we come here and get limit as b approaches infinity of negative pi halves, and we're plugging in the b and the 0. So we've got e to the negative 2b minus e to the 0. And we think about b getting really, really large. And we're multiplying that by negative 2. So we have a very, very large negative number. And if I raise an e to a large negative number, this piece is going to go to 0. So we end up with negative pi halves times 0 minus 1. So we end up with negative pi halves times negative 1. So we end up with a volume of pi halves. Okay, so on into day 2. If you look on the back of your sheet for your day 2 notes, we have this explanation. It says, if f has an infinite discontinuity at a or b, or at some c inside there, so if it has an infinite discontinuity, which is another name for vertical asymptote, inside the interval or at the endpoints, then we also are an improper integral. So we think here, at first glance, our 0 to 1 has no problems here as far as an infinite limit here. However, if we think about what the graph of 1 over x to the 1/3 looks like, we are going to have a discontinuity at x equals 0, which is at one of the endpoints. So when that happens, we have to think about a different sort of improper integral. So we're still going to use the limit, and we're still going to use, since 0 is our place where the discontinuity is, we're not going to approach infinity this time, though. We're going to approach 0 from the right-hand side, since we're going between 0 and 1, of the integral from a to 1 of, I'm going to go ahead and write this as x to the negative 1/3 dx. And I'm going to integrate. Limit as a approaches 0 from the right, and I get increase the power by 1. I get x to the positive 2/3 over 2/3. I'm going to go ahead and say 3/2 here, between a and 1. Leads me along here. We're going to use the fundamental theorem. Limit as a approaches 0 from the right. We get 3/2, and we plug in 1, and we get 1, and we plug in a, and we get a to the 2/3. Next step, we're going to let a approach 0 from the right-hand side, and we're going to use the methods we've been using all the time through limits. If we can plug in a value for a, whether it be right or left or all around, I'm going to try to do that, and I can here. We plug in 0, and we end up with 3/2 out of our limit. So again, this is a convergent improper integral. Next one. So we again have this discontinuity that happens at x equals 0. So we're going to have the same kind of idea. Limit as a approaches 0 from the right, because we want to be inside the interval here, of the integral of x to the negative 3 dx, which I can then integrate. Excuse me, I should have an a here and a 1 here. And now we have limit as a approaches 0 from the right, and we're going to integrate x to the negative 2 over negative 2 between a and 1. And then we're going to realize that if I rearrange this, it might make it easier for me to think about. So I'm going to evaluate this as negative 1 over 2x squared between a and 1. Next thing, limit as a approaches 0 from the right. I'm going to plug in the values, so I have negative 1/2 minus a negative 1 over 2a squared. I'm going to let a approach 0 from the right-hand side. This has to do with what we learned where we decided that there was sort of a vertical asymptote idea, and when we tried to plug in, we got undefined. And so we would choose something, in this case, from the right-hand side of 0 to decide on its sign, because we knew this part would be like an infinity sort of idea. So but we didn't really have to do that here, because if we think about a getting really, really small, this fraction is going to get really, really large in the negative direction. And no matter what I do, if I take negative 1/2 and subtract a negative large number, we're going to end up with a huge, huge number. And so we would have a non-existent limit, which would mean that we have a divergent improper integral. All right. Let's stop there, and I'll continue on in the next one.